Have you ever wondered why rainbows only appear when the sun is behind you? It seems like magic, but it's actually pure geometry and physics. The answer lies in understanding how light bends and bounces inside water droplets. If you love exploring the hidden science behind everyday phenomena, consider subscribing to the channel for more fascinating deep dives. Let's start with the basics. A rainbow forms when sunlight enters a water droplet, bounces around inside it, and exits toward your eye. But here's the key. This only works when the sun is positioned behind you. If the sun were in front of you, the light would never reach your eyes in the right way to create that beautiful arc of color. Imagine standing outside after a rainstorm. The sun is low on the horizon behind you, and millions of water droplets fill the air ahead. Each droplet acts like a tiny optical instrument, bending and reflecting light in very specific ways. The angle at which light must enter and exit each droplet is crucial. This is where geometry becomes absolutely essential. When a ray of sunlight hits a spherical water droplet, something remarkable happens. The light slows down as it enters the water, bending at an angle. This bending is called refraction. The light then travels through the droplet and hits the back surface. At this point, it reflects, bouncing off the inside like a ball bouncing off a wall. Then it travels forward again and exits the droplet, bending a second time as it leaves the water and returns to air. Here's what makes rainbows possible. The angle between the incoming sunlight and the outgoing light that reaches your eye is always around 42 degrees. This number is called the rainbow angle, and it's determined entirely by the physics of how light behaves inside water. For most observers, this angle never changes, which is why all rainbows appear at roughly the same arc in the sky. Now let's talk about why the sun must be behind you. Imagine the sun is in front of you. The light would travel forward, hit water droplets ahead of you, bounce around inside them, and exit. But the light would be traveling away from you, not toward you. You'd see nothing because no light is reaching your eyes from those droplets in the right direction. When the sun is behind you, though, everything changes. Light travels from the sun, passes over your shoulder, hits the water droplets in front of you. The light bounces inside them at precisely the right angle, and exits traveling back toward your eyes. This is the only geometry that works. You're essentially looking at light that's been redirected by millions of water droplets in a specific pattern. Let's visualize this more carefully. Draw an imaginary line from the sun through your body and extending forward. The water droplets that create the rainbow you see are not directly in front of you. They're actually positioned at an angle of about 42 degrees from that line. This angle is the same whether you're looking up or down, left or right. It's the same angle for every observer. This explains why rainbows are always circular arcs. If you were up in an airplane, you could see a complete circle of rainbow around your shadow on the clouds below. The rainbow is always centered on the anti-solar point, which is the point directly opposite the sun in your sky. The sun is at your back, and the rainbow forms ahead of you at this consistent, unchanging angle. The reason we see distinct color bands is that different wavelengths of light bend slightly differently when entering water. Red light bends the least and exits the droplet at a slightly different angle than blue light, which bends more. This wavelength-dependent bending is called dispersion. It spreads the white sunlight into its component colors. Red always appears on the outer edge of the rainbow, and violet on the inner edge, with orange, yellow, green, cyan, and blue in between. Each color you see comes from droplets at a slightly different location in space. The red light in your rainbow is coming from droplets at about 42 degrees from the anti-solar point. The violet light is coming from droplets at about 40 degrees. You're seeing light from different droplets for each color, all carefully sorted by the geometry of refraction and reflection. Something else remarkable happens sometimes. You might notice a fainter secondary rainbow outside the primary one. This forms when light bounces twice inside the water droplets instead of just once. The secondary rainbow appears at about 50 degrees from the anti-solar point. It's dimmer because more light is lost with each reflection. The color order is reversed in the secondary rainbow, with violet on the outside and red on the inside. Here's a practical consequence of this geometry. You can never walk toward a rainbow and reach it. As you move, the position of the rainbow moves with you. This is because the rainbow isn't actually a thing in space at a fixed distance. It's an optical illusion created by the angle between the sun, your eye, and the water droplets. If you move to a different location, the entire geometry shifts, and the rainbow appears to shift with you. This also means that two people standing at different locations see completely different rainbows, even though they might think they're looking at the same one. Each person is seeing light that's been bent and reflected by different droplets. The rainbows might overlap and look the same, but they're actually caused by different water droplets. Water droplets aren't the only things that can create rainbows. Any spherical, transparent object with the right refractive index can do it. You can create rainbows with glass spheres, dewdrops on spider webs, or even water spray from a garden hose on a sunny day. The principle is always the same. If you've learned something new about rainbows today, please like the video. I'd genuinely love to hear your thoughts about rainbows and refraction in your own experience. Share your experience in the comments below. Thanks for watching, and please subscribe for more explorations of the science behind everyday wonders.